Hello, everyone. So I'm going to talk to you today about building UI physics in Swift. And for those of you who don't know me, my name is Conrad. I work on an app called Workflow. I work on anything from our UI drag and drop animations to our sync engine. And I'm here to talk to you today about some of the stuff I've picked up doing physics in our app. So first, before I talk about building UI physics, let's talk about why. Why is it important? The reason it's important is because a lot of the UI we use today is direct manipulation. That means whether you're using a mouse or your finger, you're often dragging and dropping things across the UI and moving them around. And it's really important that these virtual elements behave like their physical counterparts. So this really helps the user understand the UI. And believe it or not, physics is actually already an integral part of iOS. Now, the classic example is scroll views. If you take a scroll view and you fling it and it slows down over time, that's the same friction that would slow down a ball if you roll it across the floor. Same thing with the notification center. If you slam it down, it bounces a little bit. It's same like dropping a ball on the ground. If you take the control center and fling it up, it behaves as if it's acting on a spring. And when you scroll through your messages, all of them are connected by little springs. And on iOS 6, unfortunately, it doesn't do this anymore. The alerts used to bounce, almost like a little spring effect. But these are all things that Apple builds for their UIs. If you're going to be building your own UI, you need to be able to build your own physics effects to add that little bit of magic to your UI. So let me show you something I built a little while ago for Workflow. So let me show you this. So for those of you who are unfamiliar with Workflow, it's an automation tool. So basically it allows you to drag and drop to build your own almost apps, but we call them workflows. So I'm going to show you a very simple workflow. We built this thing called the content graph, and this actually powers Workflow. So the idea behind the content graph is that everything is connected. So for example, an event on your calendar is actually also has a location, it also has a date, and the people invited are also part of it. So I built this visualization to help users debug. This is for more advanced users, but for example, if I pick an event on my calendar, we have this crazy graph. And I haven't worked on this in a little bit, so it's a little hectic now, but this calendar item that I'm dragging around, it has connected to it an iCal file, a maps link, a location, and a date. So this actually helps you, so you can I can tap on the date and I can see the start date or the end date, and I can actually view it right there in the app. So this is what's called a force-directed graph layout. It's a way of representing a graph with nodes and edges that's fun to play with in the UI. So I'm going to actually show you how to build your own today. So when a lot of you are thinking, okay, let's build a physics simulation, you think, okay, let's use UIKit Dynamics. And while UIKit Dynamics is great, it's not the best for every situation. And this is because UIKit Dynamics is built on a physics engine called Box2D. And Box2D is a 2D physics engine. It has collision detection and rigid body dynamics. But if we're building a simple force-directed graph layout, we don't need things like torque and collision and all of the other things that come with this physics engine. And it can actually make it hard to customize and control in addition. Because there's all these forces happening, if you actually want it to do something specific, if you've ever played with UIKit Dynamics and you want something to go from here to there and stay there and then swing around in a certain way, sometimes it's actually hard to get this to happen. So what are the alternatives? So right now, there aren't too many alternatives for physics engines out there. One that comes to mind is Pop. So Facebook's Pop is actually an animation library, but it's technically a physics engine because it simulates a spring, but it only simulates a single spring at a time. And we're going to need a lot more springs to simulate that force-directed graph layout. So it's great for one-off animations, but it can't really do a more complex simulation. So if we wanted to build our own, what's involved? So Swift actually makes this really nice. One of the reasons is Swift has operator overloading. So working with vectors like position, velocity, and acceleration, you can actually overload the arithmetic operators so that it's super easy to manipulate them. In addition, Swift has value types. And what value types basically means is that you can get this physics engine to have similar performance to something in C++ like Box 2D, for example. But where would we begin? So it all starts with something called CA display link. So by a show of hands, how many of you are familiar with a CA display link? Okay, so it's some of you. So what a CA display link does is it notifies you every time the screen refreshes. This is what it looks like. You create one, you give it a selector. This one's called tick. Some physics engines use the term step. But the idea is that every frame you want to calculate all of the new positions for every particle on the screen. So that's what a CA display link does. And these calculations essentially are calculating position. So that's actually, you want to use some form of integration, which is taking velocity and acceleration and turning it into position. And we're going to use a form of integration, very simple, called Verlet integration. This is used for a lot of computer graphics stuff because it's stable and very easy to implement. And it sounds like it's calculus because it's integration, but it's actually not. Well, it is, but this is the basic, motion equation. Position is half at squared plus vt. And I'm sure if you've taken a physics class, you've seen something like that. And this is what Verlet integration is. Now, this is the complex form. We're going to actually reduce it down to be super simple. But essentially, it's saying, take the previous position and velocity and calculate the new position and velocity. So if we assume that the time step is 1, and we take out all the constants, you can actually get it down to something like this, which is you add the acceleration to velocity every frame, and then you add the velocity to position every frame. So it's super easy to digest, especially in Swift, because that's literally what it looks like. So this form is called velocity Verlet, the velocity Verlet method. And so I'm actually going to jump into code and show you where I started implementing this. But I took inspiration from this library called D3 Force. It's part of the D3 JavaScript library. And this is what they use for force-directed graph layouts. So first, when I was building this, I needed something to represent the points on the graph, all the different nodes. So I made a protocol called particle. And every particle has a position and a velocity, and a tick method. And the tick method is used to actually set the position of the view on screen. Then I also built a force protocol. And the force protocol is representing something that manipulates the particles. And if you think about the force-directed graph layout, there's more than one force at work. So this helps me compartmentalize it into those separate forces. So I'm actually going to show you what a very simple simulation class looks like. So a simulation has a list of particles and a list of forces. And then it has a tick method. And the tick method right now is very simple. It iterates through all the forces, and it performs them, and then it adds the velocity of each particle to its position. And this is simple code. I removed the redundancies just so that it's easier to understand. And so if we're actually building this force-directed graph layout, there are 3 main forces, at least in the one I built. The first is Coulomb's law, which in the way I'm using it is used to repel every single node on the graph from each other. So that's why they separate apart. Then I use springs to connect them. They represent the edges of the graph. So we have them exploding outwards, and we have springs keeping them inwards, and we have a centering force just to keep it on the center of the screen at all times, just so that if you fling it, it doesn't disappear, because that would be terrible. So I'm actually going to jump into the physics of each of these and the actual code behind them, and show you that it's not that complex. So this is the physics behind Coulomb's law. Basically, the force between 2 particles is proportional to the 2 charges of them, and inversely proportional to the distance, that's r, the distance between them squared. Basically what that means is as the particles get farther apart, the force gets very, very weak very, very quickly. And if we assume for the purpose of this simulation that mass is the same for all the particles, we actually don't have to deal with it, and we can just remove it as a constant. So we're just going to deal with acceleration equals the charge over the radius squared. So this is the code to implement Coulomb's law. So this is a simple direct sum implementation where we iterate over all the particles twice. And between each pair of them, we calculate the distance between them. We subtract the position and then calculate the magnitude. And then we add to the velocity, which is accelerating the force based on the charge divided by the distance squared. But unfortunately, this direct sum method is inefficient. And for those of you familiar with big O notation, it's order n squared because I have to go through the particles twice. And if I'm doing this every frame, it can get very expensive very quickly because the iPhone refreshes at 60 frames per second, which means you only have 16 milliseconds to do all the calculations. So if you have 100 nodes in a graph, the simulation can get really choppy if you don't have an efficient simulator. So we can actually work around this using an approximation. So it's called the Barnes-Hut approximation. Basically, we can reduce it to order n log n, bear with me, using a quad tree. So quad trees are really cool. I'm actually going to show you how building a quad tree in Swift is super, super elegant. So the idea behind this is that instead of iterating over every single particle, we treat a bunch of faraway particles as one, so that we don't have to do as many calculations. So this is a visualization of a quad tree. The idea behind it is that you take the space of the simulation and you divide it into 4 quadrants. That's why it's called a quad tree. And then you divide it into 4 quadrants again, and you put the nodes into each of the quadrants they belong in, and you keep subdividing until there's only one node left. So you can see here where the squares get smaller, that's because that's where the nodes are. And the tree is a recursive quadrants. So in Swift, this is super easy to implement as an enum. So we have 2 cases. One is for the point at the very bottom. The point has or the leaf node has a point. And then the internal node, you can see in the associated values, it has 4 subtrees. And the cool thing about this is I can actually make an indirect case. And this is something that not too many languages have natively in their types, but what this means is if I were to have an actual recursive enum, it would be infinitely big. So indirect just means internally make an allocation and use a pointer basically internally. That's what indirect means, is use a pointer. And you see this init function. In init, I make the recursive tree. So the init function itself is actually recursive. And you might be seeing these parameters like initial and accumulator. And what those are for is to take the charge of the leaf particles and combine them and put them in the internal nodes. So the idea is that we can use an internal node as a leaf like we were trying to do by combining the forces of all the children. So every node in the tree has an approximate charge. So this is what the code looks like. Charge is represented by a magnitude and a position, the center of charge. And every tick, we make a quad tree. So this needs to be really, really performant because we're doing it every frame. And you see that the accumulator iterates over the children and combines the charge and location. And then to actually enact the force, we instead of doing 2 for loops, we do 1 for loop and then iterate over the tree. But see this return function down here, where you can actually return true and it will stop. It won't go to the children. So the idea with this Barnes-Hut criterion is that if it's sufficiently far away and sufficiently small, then we'll actually take the node and use it, accelerate the particle based on the value, and then return yes, and then stop right there. So this actually makes a huge difference by using a quad tree, and it doesn't decrease the quality of the simulation. So that was the most complex force. Springs are a lot simpler. Springs, basically, the equation is F equals kx, or the force is proportional to the distance between the 2 points times a constant. And if we assume mass is constant, we conclude that acceleration is directly proportional to the distance between the 2 points. So even though a spring is complex to solve in advance, to actually integrate it using velocity of relay, it's very simple. So you see here that I calculate the acceleration, which is the difference in position minus the distance of the spring, or the resting length, the length that we want it to be. And then we subtract it from the first node A and add it to the second node B, which means pull them together, essentially. So every frame, we just pull these nodes together. What's really cool about these forces is that if you run them every frame, they actually end up working together very nicely. Even though they're directly competing with each other, they end up making a very smooth simulation. And the last force is the centering force. And that one is even more simpler. It gets the center of all the particles, the center of it averages where all of them are, and the center of the view, and it adds that difference to every particle. So it just moves it to the center every single frame. So with all three of those forces, I'm actually going to now show you a demo and walk through the code. So if we look here, here's my simulation class. Now I added a few things here to make it easier, or to make it more production ready. So I added a fixed property to the particle, which means that when you drag it, you don't want the graph pulling it away from your finger. So it means while I'm dragging it, set fixed to yes and don't interact with it. And then I also added an alpha property. And this is to essentially damp the simulation. So over time, alpha goes down, and the intensity of the forces goes down, and eventually it comes to a rest. And this allows the graph to sleep when you're not interacting with it. And then the loop looks very much similar, still the same, just iterate over all the forces. Now I just added an if for the fixed. If it's fixed, set the velocity to 0, else, and I also decay the velocity, else increment the position. So that's that. Now if we look at the actual implementation of the particle protocol, I went and implemented it for UI view. So we see here that there's a view, and we initialize this particle with a view, and we set the center to the position every tick. But you all might be seeing this unmanaged thing. And that was not originally there, but it arose out of a performance issue, which is these particle structs, every time they're edited, are copied. Because they're a value type, they're copied. And when you copy a struct, it needs to copy all the things inside of it. And to copy an object, it needs to perform a retain on the view. So every time anything was happening in any of the simulations, it was retaining and then releasing the UI view. And that retain release traffic actually added a lot of time to the simulation and slowed it down significantly. So this tip to use unmanaged is actually in the Swift performance optimization guide. It's in the Swift repo, and I read it by chance and found this solution to the problem. And this is unsafe, so if the view were to disappear, this would crash, but I can guarantee that the view will always be there while it's simulating. So it's very small wrapper around unmanaged so that the retain and release calls go completely away. And then here's the actual implementation of the quad tree. I'm going to separate it out into big chunks. So the first case is if there's only one particle, make a leaf. If there's more, then make the 4 quadrants. And then figure out of all of the particles which quadrant they belong in. And then make the 4 subtrees. And then make the internal node. And by making these trees here, this is where it recurses. It makes a tree within a tree, and it keeps going down until it hits the base case of one node. And I also implemented a visit, which goes top down and visits all of the nodes. But originally, this is probably actually the most highly trafficked code path in the simulation because it does it for every particle, every tick. So the previous implementation is here, and I couldn't use this because it was too inefficient. So while this looks really nice, I have a children property, and I iterate over all the children. There was a flat map here. And the flat map is it's fairly efficient, but to do it every single frame all the time, it copies some memory and takes a while. So by eliminating the flat map and just manually for each child visiting it, I got another performance increase. So that's one interesting thing I've learned through this project is that awesome, like Swifty Swift sometimes isn't the most efficient, which is unfortunate. And then in the view controller, I put it all together. So we can actually just go and run this, and you can see what this looks like. I tweaked the constants, hopefully, so that it looks nice. Let's build and run. And there it is. So this is a very simple one. So you can see that when I drag the nodes, they stay with my finger, and when I let go, they collapse as if they're on a spring. And you could use this to represent a bunch of kinds of data. One I really want to see is I want to see Wikipedia clients implement something like this so I can see my history on a graph. Because I often read an article and I want to read more, and I drill down, and it'd be useful to be able to visualize it. So one thing you also see here is that if I try to move a point towards the other points, they move away. And that is because of Coulomb's law. So I can try to get them together, but it never works. And I have another demo, actually, where I actually made something like a cloth. I made a square grid. It's actually really fun to play with. Compiling Swift source files. And this is the cloth. So what's really cool about this is you can kind of pull it, and then you can actually flip it. Thank you. And something that's actually really cool, and this is just fun to play with. I mean, I could do this for the rest of the talk. But one thing that's really cool is you could actually, using a mesh transform, you could actually put a view on top of that mesh and interact with the view and flip it over as if it was a real object. And if anyone ran Ubuntu at any point and had a window manager called Compiz and enabled something called wobbly windows, they actually had this. Wobbly windows was super fun to play with, but after that I haven't seen it since. So I really wanted to create this on iOS, so I was able to just by connecting these nodes together. And what was I going to show? Oh yeah, so this is I just want to show briefly the dragging code. It's also very simple. I have a pan gesture recognizer on every little node. And when you start, I fix it. When you change the position, I set the position, and I kick the simulation because it pauses after a while, so I restart it. And then when you let go, I unfix it and actually give it the velocity of the gesture recognizer. And that is it. Does anyone have any questions? I'm actually going to post all this code to GitHub so you guys can play around with it and edit it. Yeah, let me know if you have any questions. Benjamin.
Someone have a question? Oh. Firstly, really great presentation. Thanks a lot. And the question was related to the 3D aspect that you mentioned, flipping the view. Would you have to like infer that based on the movement of the particles, because they are represented in a 2D space, so they didn't really have a concept of 3D. Did you think through how you would actually do that, or?
So I actually didn't think about it. At the time, I had just assumed that if you move that corner over there, it would flip it, but it would actually rotate it. So right now, it doesn't handle 3D, but you could probably implement this in 3D just by changing CG point to a new type with 3 positions.
Thank you.
Yeah.
Any more questions?
So one question I have is, you're assuming that the display link frame rate will actually be hit at the same rate, like it's gonna be fixed time step, which is, like I used to do game dev, so I kind of relate to all of the things you talked about, which is also a very great demo. My question is, does your implementation, the actual like workflow implementation, takes into consideration the fact that you might not be reaching the same time step, because that has to use delta time, and it's a little more complicated. So I'm wondering whether...
It doesn't handle that currently in terms of handling time steps of varying length, but it can. It was just for simplicity, I removed the timestamps. But yeah, that's something you can definitely do. The goal, though, is actually to just hit the frame every time.
Yeah, sure.
And it is possible if you have like a small number of nodes, but as you get bigger and bigger, it gets more complex.
Okay, thank you.
Yeah, no problem.
Right, I guess that's it. Thank you, Conrad.
Awesome.
Thanks.
Thank you.